Hey guys, welcome. This is our recap of Tuesday/Wednesday's class. That's January 4th and 5th. So let's get started. So our focus was algorithm efficiency in this first one. And this one, hopefully you watch carefully because a good concept that they test on the AP exam, something that we don't normally will use frequently in our use directly when we code, but a good, nonetheless, way of thinking how could we solve a problem more efficiently. So, like I said, make sure you are writing all this stuff down. If you didn't, please go back and do it. So first thing I want you to write about is, have you ever lost a pencil in your backpack? What are the steps you take to find out, to find the pencil? So if you were specific, I have students that write, step 1, unzip your backpack. Step 2, search the main compartment. Step 3, say unzip the smaller compartment, or take out my binder, look in my pencil pack. I had one kid that says, 1 step, dump all my stuff on the floor. Probably not what he does when he looks for it. But you could write these out in very specific steps, and everyone's probably going to have a different way of doing it, but there's probably more efficient ways to do it. And so our activity that you guys were supposed to do was to go to Code Studio, generate a random ticket, and write that number in your journal, and then you were also going to write it on the Google Sheet that this would take you to. So I'm just going to go to the Google Sheet, and so you guys put them all in, and the winning number was 907, and what I wanted you to do was to essentially go through and check for who won the ticket. Once we have everyone's ticket number in, who won. So we would go through and I'd say, okay, Kate, Gianna, Claire, Aiden, and I keep going and I'm just checking each one and I'm seeing, oh, Christian, you're really close. And I'm just seeing who won. Oh, Jordan's very close. And Ryan Smith, 420. Hilarious, guys. I'm going to look that up. Who wrote that down? But no one over there got it. No one over here, I don't think got it. I looked at this before. 912, close. Okay, and I don't think so. We can check through period 2 and period 4. We can look through and see who had the number. Ooh, 909. I think Brad is the closest. He's only 2 off. But we can go through and we can see who won by checking each one. Inside, you better not have been gaming. That's pretty messed up. Probably someone wrote that just to have me read that. So, how many steps did it take to find out who had the winning ticket? Well, it literally took me 1 step to look at each one. So, depending on how many people there are, probably would take more times. So, if we had 6 people only doing it, it should take 6 different steps, right? Look at first person, compare it. Look at the second person, compare it. Look at the third person, compare it, so on and so forth. Oh no, my battery is running low. I must plug in quickly. Okay, I plugged in. We're good. So yeah, if we had 6 volunteers, it would take 6 steps. If it was the whole class, which we just did, it would take however many people were in class that day. If it was the whole school, it would take everybody. So what's the pattern is for each additional person, it takes another step. And so what we would see is we'd see something like this. So for each instance of a person, so if we did 3 people, it would be 3 steps, 6 people, 6 steps, 10 people, 10 steps, 10 and 100, 100 steps. So we would call this a linear type of pattern that we would see. So with a partner, I asked you guys to try this, is to generate 7 different tickets. So here's the example: 117, 232, 245, 410, 705, 716, and 833. Organize them in numerical order. Copy one of the numbers onto a separate, it says sticky note, but you can just copy it anywhere. This is the number you're searching for. So you know the number is going to be in there. So you're going to take 7 numbers, order them, pick one of the numbers, and you're going to search for it. Okay, so the goal is, and here's the challenge, create an algorithm to determine, and here's the hard part. Since I wasn't there, you probably just skip to the next page. But this is where the real learning comes in. How well could you come up with something? And this challenges you in a very different way because there's no direct way that I'm telling you how to solve. I'm just asking you, could you solve it? So you're going to determine how many different steps it would take you. So the search can start at any of the sticky notes. You can start first on the left. You can start the first on the right. You can start in the middle. You can jump over. It says sticky notes, but those are just the numbers. You can jump over numbers. You don't have to search them in order. You can determine which numbers to search next based on the one that you're on. So you could do some sort of like comparison operator like we have. And the goal is to make the determination in the least steps possible, but don't forget your number could be anywhere in the list. So obviously if it's the first number in the list, it's going to go really fast. If it was the last number in the list and you said to start on the first one and check, then that would be the worst possible case would be 7 steps. So what's the greatest number of comparison steps it would take to find any number in your list using your current algorithm? So I asked you to take 10 minutes to try this. Then share and compare. Now, this is the one that we would recommend. Okay, this is what we call the binary search. It says find the middle number in the list, compare that number to the given number. If the number is less than the given number, remove all the cards to the right because we know that it's not that number. And if the number is more than the given number, remove all the cards to the left, including the middle number. Then find the middle number in the shorter list, and then follow the steps again. So it's kind of like a loop. Find the middle number in the new list, in the new shorter list, follow the instruction step 1 for comparing. And you have found your number. Look through these next slides. This is our binary search. So here it goes. We take 705, we compare it to the middle number. That was step 1. It's greater. Okay, so we know that all the numbers to the right are where it's probably going to be, so all the numbers to the left, we eliminate. Okay, step 2, we compare it to the middle of what's left, and we run the same thing. It's less than, so we're going to get rid of everything to the right, and boom, step 3, we compare, and that's equal. So we were able to do it in 3 steps. So this is a binary search. It utilizes the fact that we have numbers in numerical order, and so it's a lot faster to do it this way because we know information about how the list is organized. So now it says try the binary search for different instances. We've done a few for you. Copy the instances in your journal and plot the points. We just did 7. That was 3. If it was 1 instance, meaning you have 1 number and you're trying to find 1 number, it's going to take 1 step. 3, still take 2. You'd have to do first step, find the middle, less than or equal to, and then second step you'd find it. So for 5, it's 3 steps. For 9, it's 4 steps. And for 15, it's 4 steps. So now we have a graph that looks something more like this, which is less than what we would call a linear. Okay, it's growing slower than a linear. And then here's another way of thinking this, and this is where we see the pattern. How many bits does it take to represent 1 in binary? The answer is 1. What about 7? Well, it would take 3 numbers in binary, right? 1, 1, 1. And 15? That's 4. And actually that's 1, 1, 1, 1. And so those would be the ways that we'd represent these numbers. And it also refers to how many binary digits we have. Hence why we call this a binary search, because it follows along with binary. So we have our 2 search algorithms we've explored. The first is linear. As we did more inputs, the number of steps increased at the same rate. But in binary, it grew at a much slower rate, like this. It's still faster than doing a linear search, but the data has to be sorted, so that's very important. Okay. So if I had 1 input, which algorithm would I want you to get my answer with the fewest amount of steps? If I only had 1 input, either one doesn't matter, linear or binary search. If I had 5 or 100, binary search will be faster. So efficiency is a measure of how many steps are needed to complete an algorithm, so we want to be more efficient. Linear is going to check each one in the list until it finds it. Binary search is going to look at basically the middle and has to be sorted values. It will look at the middle and then remove half the data and then repeat that until you find the final answer. Okay, the second part of the day was focusing on unreasonable time. which you might think this video is being unreasonable. But what does it mean to be more efficient than another? And that would probably be less steps. That's what I was hoping you would say. So we're going back to this. You have a winning number is 1,000, and it says generate a ticket. Silently move around the room, no talking. See if you can find a winning partner. Okay, so and again, the way you win are the two ticket numbers add to the winning number. So if I had 500 and someone else had 500, we're winners. Okay, so that's what you're supposed to do. The second one you're supposed to do, if this worked out, is you can pick the winners are any group of from one ticket all the way up to all of them that add to the winning number of 2,500. So maybe I think the number goes up to 999, maybe it's 1,000. You probably need at least 3 people to hit this. But if you were to try and do this, you can now talk, so you can find people and add them on and see if you can get this, and see if you can become part of a winning group. So which raffle felt like it was more difficult? Okay, I hope you thought the second one was more difficult. Even though you can't talk in the first one, all you had to do is find one specific number. So you just had to look at their thing, you would know automatically it's not. Versus the group winning, you'd have to walk through and talk to many people and try and finagle your way there. So we could write an algorithm that goes through every possible check for the pair raffle or the group raffle. And let's see how many checks there are. So with your partner, you're supposed to fill out the 2 tables on the activity guide, and there was the link for the activity guide. You're supposed to share your responses, and then with your partner, discuss the next couple of slides. So when we do a pair raffle, this is what our graph looks like. 2 tickets, I have to do 1 check, 3 tickets, 3 checks, 4 tickets, and so on. And so the formula for this is n squared minus n divided by 2. We don't have to remember this formula or anything, but this is telling us how quickly we are going to have to increase the number of checks by tickets. Okay, and so as you can see, this is what looks like a parabola-ish looking graph here. It's increasingly going up, we would say it exponentially. The group raffle appears to be going up even more. This one is squared, n squared, so we call it a polynomial. This one, since 2 to the n power, this one is actually exponential. It's going to be going up a lot faster if we compare the two between the pair raffle and the group raffle. And the group raffle is because we had to check multiple people just to get to one correct answer, to get that higher number. And so here's another way of thinking of it. The number of checks is the largest number you can make with that bit. Okay, so with 1 we can make 1. With 2 bits, the biggest number we can make 3. With 3 tickets or 3 bits, we can make the biggest number, our value of 7, and so on and so forth. And so polynomial and exponential both curve up. Why do we think only exponential is considered unreasonable? So we've done the linear one. We did the sorted raffle. We did the binary search. That's actually would be a log. Most of you probably noticed that. The polynomial was our pair raffle. But then the group raffle is exponentially. So why do we consider that one unreasonable? And just by looking at this graph, the answer should be clear that it's going to get bigger faster than any of these other ones. And that's going to create a problem for our computational. Now again, computers are getting faster and faster and faster, but that doesn't mean something that can still rise at an exponential rate. It might be hard for it to still keep up with. And here's an example. Okay, so if we look at the number of tickets, we can see what we would see is how many checks. So right, 10 tickets, sorted raffle, normal raffle, pair raffle, group raffle. So sorted raffle, 4 checks, normal raffle, again, it's going to be the same amount of checks as tickets. Pair raffle, it's polynomial, and then exponential. And we see that the number for exponential just gets crazy, crazy, crazy big in comparison even to the polynomial one. Just looking at step 2, we see 400 checks, which is a lot, but this is over 1 million already. That is an extremely larger amount. And these numbers right here, I don't know if you can even put your brain around it, but they said this right here, at this point there are more checks than atoms in the universe. Right here. And that's just to do 1,000 tickets. Okay, so 1 million checks for a pair raffle for 1,000 tickets, it's more atoms in the universe. So we can see why exponential is getting way too big, way too fast. I don't care how fast our computers are. It's going to take a long time for them to catch up with something like that. So overall, reasonable time, algorithms with a polynomial efficiency are lower, which constant, linear, square, cube, are said to run a reasonable time, but algorithms with exponential or factorial efficiencies are example algorithms that do not run in a reasonable amount of time. So, your school is considering running a group raffle at an upcoming assembly to give away a prize. Write a brief explanation of what advice you'd give them, and I hope the advice was, don't do a group raffle, ever, because that would be way too hard. Alright guys, that's it. Thank you so much. See ya.